our cosmic origins. Located high in the Andes mountain range, the 66 antennas that make up the Atacama Large Millimeter Submillimeter Array, ALMA, are an imposing sight. Under one sky, more than 20 countries embark upon a scientific endeavor that can only be realized through collaboration. North America, Europe, East Asia, and Chile work together to answer humankind's fundamental questions. Northern Chile was chosen as the site for ALMA because the Atacama Desert is the driest in the world. Its atmosphere, almost devoid of water vapor, enables detection of some of the faintest signals from the universe. Over 16,500 feet above sea level and covering distances of up to 10 miles of the Chajnantor Plateau, the ALMA antennas work as a single large telescope. A supercomputer combines and synchronizes all of their signals in real time. Thanks to this engineering and scientific feat, we're learning about the cold universe, the secrets of planet formation, and the chemical elements that constitute the building blocks of life. Professionals from around the world work for ALMA, pushing the limits of knowledge every day. In Chile, about 50 staff members are based in Santiago, while another 200 work in shifts at the Operations Support Facility close to the town of San Pedro de Atacama. Most of the staff works in the offices, laboratories, and antenna control room of this facility at an altitude of 9,500 feet. Others ascend to the Chajnantor Plateau at 16,500 feet to maintain and relocate the antennas, among other tasks. Strict safety protocols are crucial under these conditions. Thanks to leisure and residential facilities, staff can lead a healthy lifestyle, playing sports and games, watching movies, enjoying nutritious meals, and resting in comfort. ALMA plays a key role in global astronomical efforts. Along with other radio telescopes, it allowed the first image of a black hole to be captured. Without ALMA, that goal would have been unattainable. The Chilean astronomical community actively participates in ALMA research and discoveries, using its 10% of observing time. The radio telescope also contributes to workforce development and supports national and regional scientific, technological, and outreach projects. An example of the latter are the thousands of visitors who tour the facilities each year. ALMA respects the local Licanantay or Atacameño indigenous culture, supporting educational and other projects in the town of Toconao in San Pedro de Atacama, preserving archaeological heritage sites, and protecting the unique flora and fauna of the region, to name a few initiatives. Mirroring the antennas that work in unison with one goal, under the same sky, the international collaboration that ALMA embodies continues the search of our cosmic origins.
Hey everyone, welcome to our virtual tour today. Today we're having great guests that are joining us for the subject. First of all, I want to introduce myself. My name is Thais Mandiola. I'm part of the EPO team, the educational outreach program that we have. So today We're talking about these subjects, the very interesting ones, the correlators and the receivers. This is a very complex chain of reception, conversion, processing, and recording of astronomical signals. They're leading technology that is also helping to improve the sensitivity of other radio telescopes that we have in the world. Before we begin, it's important to clarify that at this moment and for a year ago, we're not having any visits to the observatory due to the pandemic. And now ALMA is not 100% operating, but our interviewers will be able to tell us more about this and what is going on at the OSF there in the north of Chile. Today, we have around 260 people working in ALMA, but few of people know really that 80% of the staff are Chilean, and that 65% of the staff work in the facilities where we're seeing here in the video at the OSF and the AOS where the antennas are located, near San Pedro de Atacama. But well, going into today's subject, as mentioned before, the correlator is one of the most powerful supercomputers in the world. And without a doubt, the only one located at 5,000 meters above sea level. ALMA has 66 antennas, but each one of those don't work by itself, don't work alone. To be able to form images for millimetric wavelengths captured by multiple antennas, we need absolutely superb computer power that has a capacity equivalent to millions of laptops. To be able to perform the same number of operations per second that ALMA does. To exemplify this, your eyes are connected to your brain, no? Through fixed bunches of neurons. These optic nerves carry the signals from your retinas to your brain. Your brain processes the signals and turns them into a beautiful three-dimensional view of what is around you, yeah? It is important that signals from your left eye come at the same time for the ones that are coming to your right eye. At the same time as the signals from your right eye, otherwise your vision of the world will be totally blurry. More or less, the same happens with ALMA. ALMA's eyes are really these 66 antennas. They are connected to the brain, a giant supercomputer, not by our neurons, but by tens of kilometers of fiber optic cables. These cables carry the signals from the ALMA receivers to the main computer, called the correlator. So for more about the specialty of this mega computer, we have a very important guest today. Let me introduce you to Lorenzo Martinez. He's an electric engineer from the correlator. Thank you so much, Lorenzo, for being with us today in this tour. I know that you are in your descanso, your days off. How are you, Lorenzo? It's not shown yet, but well, he's going to help us to learn more about the knowledge of this mega computer. Other of these great instruments, there you are. Hi, Lorenzo.
Hello, good morning.
How are you?
It's a pleasure to share with you this tour.
Thank
I would like to
you.
talk to you about the correlators, unique pieces of equipment as far as they design, especially for their intended tasks. And apart from being very complex machines, they are very demanding too.
Yes. So now you are in your descanso, so thank you for having to join us today. So for another hand, we have another very special instrument. There are the receivers, as mentioned a little bit earlier. They are also located in the front and located in each one of the antennas, actually, to work properly. They must reach a very low temperature. We're talking about 4 Kelvin degrees, 4 Kelvin. This is nothing less than 269 below zero. The system will become the retina of ALMA, with the ability to absorb the light with which we observe the universe. For this, we have a very special guest too, that is Giorgio Siringo. He's a senior radio frequency engineer and front-end technical lead. Giorgio is on vacation now, actually. So thank you for joining us on your holiday from Italy. How are you?
Fine, thank you. I hope you can hear me well.
Yeah, we hear
It's
you.
my pleasure. It's my pleasure to participate in this kind of activities and to share a little bit of to the public, right? To explain a little bit how ALMA works and what we do on everyday basis, right? What is our work actually to put this giant machine in operation and being able to get this very faint signals from the sky and then to do our astronomical research.
Definitely.
So I will talk about the front end and the receivers.
Yeah, and this is what for public, just to be closer to what each one of you are doing up there at the OSF or the AOS, and get into more of the detail of these instruments. They're very special ones, no? So, well, Giorgio and Lorenzo, they're specialists in these instruments, as we said. And before getting into these details, it would be interesting to, if each one of you really tells us, how was your journey to get to ALMA? How did you were able to arrive to this huge observatory? What was your career option and all of this? If we can start with you, Lorenzo, please.
Okay, I studied civil and electronic engineering in Santa Maria University here in Chile.
Mm-hmm.
My original background was in communications, but after working in some communications companies in Chile, where I had the opportunity to design the first TV cable network in Santiago, later I immigrated to Cerro Tololo, an astronomical observatory. That's an optical observatory in La Serena.
Mm-hmm.
And from there, I moved to defense company. I was there developing some radar projects, and later applied to a pipeline, and finally I found an ad in the newspaper offering a position in ALMA, so I was enthusiastic about that, and I applied and I was selected. So it was very good for me. Internally, at first, I started here in the company by assembling the antennas and the antennas electronics, actually the back end. And so later, I moved to a correlator engineer position. And I have been working here for the last 8 years.
Great. What about you, Giorgio?
Well, I am Italian, so I'm actually working in Chile, but I'm coming from far away. And my journey, as you said, it started in Italy, of course. I studied physics at the University of Rome, and I graduated at that university. And then after the university, I moved to Germany, where there is one of the most important centers for radio astronomy, which is the Max Planck Institute for Radio Astronomy in the city of Bonn. I did my PhD in astronomy there, and then I worked as a postdoc for roughly other 6 years in Bonn. And during that time, I was working at the Apex telescope, which is located on the side of ALMA, practically on the same plateau. So I was traveling from Bonn to Apex, to Chinantor, to the ALMA plateau, practically on a regular basis. Until at some point they offered me an ESO contract. So with the European Southern Observatory, I had the opportunity to move to Chile and to start working as an astronomer at Apex. And after a couple of years, ALMA started to be more attractive, let's put it like this. And I think was a sort of a natural move, and I moved from Apex to ALMA. And as Lorenzo said at the beginning, we were involved in the construction phase. So we were actually building ALMA. We were there doing all the tests and whatever was possible to assemble this giant machine. And then starting from, I think, 2013, we started science operation on a regular basis. And so then I moved to the engineering department where I am now. And I work in the role of a senior radio frequency engineer. Mm-hmm. Although my background is more for astronomy and physics. But I try to do a sort of a link between the Department of Science and the Department of Engineering. So I try to cover both aspects of the project.
Great. It's a great journey for both of you to get to ALMA, yeah. So, Lorenzo, first, knowing that the observatory is not running really 100% now, how has it been in the case of the correlator to get it activated again at 5,000 meters? Sometimes snowing up there. What has been really necessary for the conditions to activate the correlator?
Well, the correlators are very complex machines. They are unique pieces, as I told you before. Its care is very delicate, as this is not something that we go to the hardware store and buy another. Mm-hmm. We have spare for most of the parts, but still we have to be careful as far as they are very expensive. Mm-hmm. After the pandemic, the observatory shut down from previous year. It took us about a month to set to work it. We had to deal with machine that was shut down and below 0 degrees conditions, notwithstanding it was inside of a building. Mm-hmm. So special care was exerted in order to inspect every possible factor that would imply a fail before press the start button. Room ambient conditioning, possible condensed wet on components, electrical conditions, electronic power conditions.
About that, Lorenzo, what is the temperature inside of these rooms needed for the correlator to run?
Normally, the temperature is around 15 or 16 degrees Celsius.
And I understand it's about a humidity level too.
Yeah, the humidity is it have to be maintained at about 40%. Outside of the building, the humidity is around 5% or so. That's the reason why ALMA is where it is, because we have very low level of humidity. So we have to have very powerful machines, air conditioner machines that humidify the air and also keep the temperature, the required temperature for the machine to operate. Mm-hmm. Finally, after start to work, even we took all the cares. Always there are components that fails in the machine. So apart from start up the machine, we had to repair several cards that were for some reason where, for instance, one of the ship's legs unsoldered, and so would fail. So there are many possible factors that will make them fail.
Mm-hmm. And at the moment now it's running, it's active.
Yes.
It's actually good. That's
yes,
good
it's running and it's running very well.
Great news. How about the receivers, Giorgio? What's the case for them to reactivate and start observing again?
Well, the process was done in parallel, practically, as to the correlator and everything, right? So I should mention that during regular operation, we have a plan for maintenance, right, of the receivers, of the front ends. There is a schedule, let's say every 1 year or something like this, we have to do some type of maintenance. And of course, during the pandemic shutdown, this was not possible for 1 year, roughly speaking. So when we finally started the game, so the power generator were powered up, we didn't know what we were going to find, right? Everything was frozen for several months. And so there were actually some surprises. We find something that we didn't expect. Actually, we learned also something new, and we could somehow improve our maintenance plan. And there were three months, I would say, January, February, March, were very intense of extraordinary maintenance to put everything again in operation. And then by the end of March, we were able to start again with actually science observation. And if you think these are, roughly speaking, 3 months, very intensive maintenance tasks. But it was amazing that in just 3 months, we were able to put in operation again and do science observation with 32 antennas at the beginning in such a short time, actually.
Yeah, phenomenal. Great teamwork there. Yeah.
Really.
Yeah. Well,
they did an excellent job.
To have a better perspective of these instruments that you work with, if you could explain, Lorenzo, what is the correlator and how does it work, this mega computer?
Well, I try to put it in simple words. Let's suppose we are in a stadium, plenty of people, like in the old times before pandemic, and we want to hear two people conversations at the other end of the stadium. The antennas will get the point in which they are talking, but the correlator will provide the ability to discard most of the noise of the other people talking around, concentrating on our target voices and making them clear. Of course, we are not trying to hear voices in our observatory. We are a little bit crazy, but not enough. But the talking of atoms, molecules, and particles in the space, which produces electromagnetic waves that move across the space for millions of years until they reach the Earth. From their chat, we can discover how they move, how much they are, their distribution, their speed, etc. And we can, through mathematics, transform it into science data to make images and study the way in which galaxies are formed, or planets, or how the black hole behaves. In summary, try to discover our universe origin.
Great.
Well, the correlator takes advantage of the interferometry properties to convert the signals coming from antennas into data that contains information of amplitude and phase of such interferometry process. And this will allow scientists to get their study objectives through imaging, spectroscopy, polarimetry, and astrometry.
Yeah, no, it's a magnificent computer, the one that they have up there. It's 5,000 meters. Now there's a little bit of snow, I know, up there, so it's working on harsh conditions, as usually in winter time. So it's great that soon we'll start back on track. And we know that there are very important components that are related to this magnificent computer. The maser and the optic fibers that we saw in one of the videos going around there. If you could tell us a little bit of how they relate between to be able to work for the correlator.
Well, the observatory is like a giant clock. Everything needs to be fully synchronized. A maser with a stunning precision of 0.45 nanoseconds over 12 hours allows to generate the timing for all the reference signals and frequencies of the observatory. The central local oscillator of the observatory is in charge of generating and distributing all of them, all the signals. While observing, all the antennas should have exactly this. Where we are observing, all the antennas should have the same observing frequencies. They should provide a reference timing in order to align the data with a precision in the order of nanoseconds. As far as the Earth is rotating, the relationship between the signals arriving at each antenna dishes are changing very fast in time, depending on their sky position to their position on the ground. So the data needs to be delayed accordingly in order to produce the desired interferometry. Delays in the order of 15 picoseconds, that means in the order 10 to the minus 12 of a second, are applied to the antennas data in order to keep them contemporary with other antennas data. We need that in order to make a proper correlation. All the data.
Numbers, no?
Sorry?
Really big numbers that we're talking about.
Oh, yeah. Actually, we are moving between very huge numbers of millions for light years and nanoseconds, picoseconds, or whatever. So actually, it's a very wide range of things that we have to manage. We distribute all the signals through a wide network of fiber optics that reaches all of the antennas are
connected to.
Claro.
Yeah.
To transmit the observing frequencies and timing to the antennas. Mm-hmm. And also, the antennas retrieves with data, digital data, to the correlator. To have some orders of magnitude, each antenna produces 120 gigabits per second of data reaching to the correlator. Mm-hmm. But only 96 gigabits per second are of payload data. That's useful data. The rest are part of the information used to synchronize the data, check data integrity, and report antenna timing. The data contains the digitized data of 4 baseband pair of 2 gigahertz signals. Probably Giorgio will talk about the production of these basebands.
Yeah. And
then the signals provided by the front end and the back end are later sampled at giga samples per second in the antenna, and then they are transmitted to the correlator.
Perfect. Yeah, that's a great journey too. From the signals going to the correlator for, I don't know, maybe kilometers and kilometers of optical fiber, to be able to join all that information. That's what this huge machine does, no? So in the case, Giorgio, what is the connection of the correlator with the receivers? We have mentioned a little bit earlier, but if you can go more into that.
Well, yeah, the ALMA is an interferometer, right? So when, as I mentioned before, I started to work as an astronomer at APEX. The APEX telescope is what we call the single dish. So it's a single telescope that just looks at the sky. But ALMA works in a different way. So it can work also, you can use an ALMA telescope as a single dish telescope. And actually we do that as well for some science projects. But the most important application of ALMA is when we do interferometry, so that we collect the signals from several antennas. And as you mentioned just a moment ago, they are streaming. That's this huge amount of numbers digitized in the antenna, then are streamed through the fiber optics, and they arrive to the correlator at the same time. And the correlator has to handle this large number of bytes of numbers, and they have to crunch them in real time, simultaneously. And so the receivers, so let's say the eyes of ALMA, now we go back to the example that you made at the beginning of the introduction that you gave us. When I look with the two eyes, of course, the information from the two eyes, they arrive to the brain at the same time. Otherwise, I will see a lag between the two pictures, right? Mm-hmm. So everything has to be synchronized. And this is a very important aspect of the interferometry. Otherwise, it doesn't work. Mm-hmm. And the purpose of this actually is to remove the noise, the electronic noise or some other kind of noise, and extract the signal that's really coming from the sources in the sky. Even atmospheric noise is not synchronized, right? Whatever is synchronized is what arrives really from the source in the sky that I'm looking. But to do that, we have to guarantee that the receivers in each antenna, they are also synchronized among them. So they have to be all connected together with the correlator to the same clock. As Lorenzo said before, we have, like ALMA works as a giant clock. So everything is locked together, and we have to guarantee this down to nanosecond accuracy. So the signals coming from each of the receiver from the different antennas, they have to be what we say is they have to be in coherence. So they have to keep the information of the phase, and the phase difference, let's say, or the phase error when the signals arrive, they have to be coherent between them with the smallest possible error in time, let's say. Mm-hmm. And these are usually in the range of few nanoseconds. So to guarantee this is not trivial as a task. So we have to keep a local, what we call a local oscillator inside each antenna, which is locked to the atomic clock. We have an atomic clock in the central building, which is the same building where the correlator is, which is a hydrogen maser. So practically we use the transition of the hydrogen molecule to have a very accurate reference for frequency and time. And then we distribute this information to all the antennas. So we try to keep as much as possible the receivers synchronized between them. And then we collect this information back to the correlator with the signal from the sky. And we guarantee that this information arrives synchronized to the correlator. If this process doesn't work, we won't be able to do interferometry.
Mm-hmm. And you mentioned, well, in the beginning, we mentioned too about this cooling system that has the front end. It's a minus 269, right?
Yeah,
so
maybe even lower.
Maybe even lower. So if you can talk us through why is that temperature inside of the front end for the receivers, and how do you get to that temperature?
Okay, well, the main reason to keep the receivers very cold is that, as I mentioned just before, is that when we look at the sky, we don't only receive, let's say, the signals that they collect with the antennas, and then we send it to the correlator. There is, of course, the information from the astronomical signal, the information that we want to collect from the stars or from the clouds or whatever it is, the sources in the sky, which is the science target. But this signal that we are interested, it's actually embedded in what we call noise. The noise is other signals which are not interesting for us, and they are produced locally, produced by the atmosphere or produced by the antenna itself that is moving, produced by the electronics, produced by the receiver itself. Mm-hmm. So this noise, a good component of this noise, can be suppressed by lowering the temperature, because the higher is the temperature, the higher will be the noise. So on the other side, if we lower the temperature very much, we suppress the noise, and so we are able to extract the signal that we want to see, they want to detect, which is very weak usually. Mm-hmm. So this is a very important step. So the colder is the receiver, the better will be the extraction of this very weak signal from the general noise, especially of the electronics of the receiver. So the temperature of operation of these receivers, usually it is between 3 and 4 Kelvin, which means 270 or 269 below zero, right? Just 3-4 degrees above the absolute zero. It's very cold. So, and as I said, this is the main reason why we do it, to suppress the noise. But there is another reason. And this is that when we are at this very low temperature, it's possible to use some special materials that they have some special properties, which call this superconduction. So practically, for some of these metals, when they go so low in temperature, they don't have any electric resistance anymore. So some electric current can circulate practically without any dissipation in this circuitry. And this has a double advantage, that we need to use less power to power up these receivers, and there is less heat dissipation inside the cryostat, which it's a problem. If you want to keep it very cold, you have to minimize as much as possible the heat that you put inside the cryostat. And talking about this was your second question. So how do we manage to get this very low temperature?
Yeah.
So the receiver, all these electronics, they are inside a big tank. We call this the cryostat, which is practically has the purpose to isolate these electronics, these devices from the external ambient, right? And there is a room temperature outside, and there is a cooling machine. We call this the cryo cooler, which is connected to the cryostat. And inside the cryostat, there are 3 shields. So the cooling machine produces 3 different layers of temperature. The first layer is 100 Kelvin, more or less. And this is the first shield, right? So this shield receives the energy from the room temperature, from the ambient. And this energy goes through the cooling machine, goes outside, we remove it. Then there is an inner shield, which is at 15 Kelvin, which is already very low temperature. And this receives only the energy coming from the shield at 100 Kelvin. It's like an onion, right? It's shielded, one shield inside the other one. And so the inner shield doesn't see the outside, it just sees the shield which is just above it. And then there is the last stage, which stays at between 3 and 4 Kelvin, which is where actually the receivers they are. And so the receivers, they can operate at very low temperature, and they are completely isolated from the outside world in terms of thermal conduction, thermally isolated. To guarantee this also, we have to produce very good vacuum inside. Because if there is a little bit of gas, of air circulating inside, this will produce like a thermal connection from the outside to the inside, from the outer shield to the inner part. So we have to put a very good vacuum, and then we can cool down the system. Typically, because this container is very large, and there is a lot of material, a lot of metal, copper. So to cool it down usually takes 2 days. Even if we have some of the most powerful cooling machines available as a technology nowadays. And these machines, the principle of operation is actually very similar to what we use on everyday life, let's say, as air conditioning or even as a refrigerator.
Yeah.
So the principle is the same. So there is a compressor that somehow is able to push the heat from the inside to the outside. So we just take the heat from inside and we put it out. We put it outside, and slowly, after 48 hours, we are able to get to the receiver to the operational temperature of between 3 and 4 Kelvin.
The final temperature, yeah. So Nicolas is telling me that we have some questions from the public. So let's see what are those. After M87 black hole imaging, any other black hole imaging is planned for the future?
Should I answer? Or
Go ahead.
I don't know.
If you have information about that.
Yes, I have some information, because there was a meeting actually yesterday where we were reviewing the future projects of ALMA. I have to say, this is not really technology. Well, some marginally is also a technological issue, but this is more a science project. Mm-hmm. So we have to mention, first of all, that the ALMA is participating in the larger collaboration, which is called the Event Horizon Telescope, which uses interferometry, but in a more, let's say, global way, more planetary way. So the interferometry during the observation of the black holes is done not only between the antennas of ALMA, but it's done between telescopes in different places in the world. And we collect this way some sort of a telescope as large as the planet. Because there is a telescope in Spain, another one is in Arizona, the other one is in Hawaii, and we are ALMA, we are in Chile, so we practically cover the whole diameter of the Earth, and we look at the same source simultaneously. In this case, of course, there are no fiber optics connecting the telescope, so we rely on our atomic clock. Each telescope locally has an atomic clock, and then we do the correlation is done offline, so it's done later on. We have to collect all the data, and we have to believe that the data they have been taken with the same timestamp, with the same timeline. And usually this works very well, actually. So what is going to happen in the future is that we are going to change a little bit the frequency. The famous picture of the M87 black hole, that one was done in the ALMA receiver band 6, which is roughly speaking 230 gigahertz. And now we are working on the, let's say, this is also a technological challenge. So we are trying to use a higher frequency. The problem with going to a higher frequency is that we get more noise. So because the frequency is higher, so the phase noise is a bit higher, so it will be a bit more difficult to extract the signals. But this is the next challenge. And with the higher frequency, we hope to have a better resolution and also to have a more intense signals. And one of the black holes that we are observing actually has been observed even this year, I believe, in April 2021, immediately after the beginning of operation of ALMA, after the pandemic shutdown. We had the Event Horizon Telescope campaign, and we have been observing the black hole at the center of our galaxy, in the Milky Way. So to answer the question from our friend, I think is probably the next results will be related to the black hole in our galaxy, very likely.
Yes, very much.
Sagittarius A star.
Sagittarius A, yes, we expected. We have any other questions, Nicolas? All the antennas are used as one, but could it be possible to use one or more, like 5 or 6 or 10 antennas in parallel, simultaneous observation? Lorenzo or...
All the antennas are used as one. We have 66 antennas, and we are able to use at least 64 at the same time because of the correlator's limitations to 64 antennas. But we are also able to use smaller numbers of antennas. For instance, we can use subarrays. We call them subarrays. In one array, in one subarray, we can consider, for instance, 10 antennas observing one target, and we can observe in other subarray. We will be observing with another 30 antennas, another target. So we are able to, we have a very big flexibility. But the best results are when we use all the antennas. I don't know if we are responding to your answer.
Well, maybe, Lorenzo, you could mention also that we have 2 correlators, right?
Oh, yes, of course.
Yeah, they can work in parallel.
Yeah, also. Part of that, we have 2 correlators, yes. We have a big correlator that is able to manage 64 antennas, and also we have a smaller one that is able to manage 16 antennas. Normally, they can be used in parallel, and their data will be complementary in some kind of observations.
Perfect. So we're going back a little bit with Giorgio about the receivers to talk through more about how many bands are inside of this cryostat. Yeah, did you mention how many do we have and the frequencies that are able to study with these amazing bands?
No, I didn't mention it. Right, but I mentioned, for example, we use band 6, right? For the it's just a name, band 6. So, but of course, we should give more information about this. So, this big tank that we call the cryostat, it can hold up to 10 different receivers, right? 10 bands, what we call them. Why do we call these bands? For a simple reason. When we look at the sky, we have to think that for any ground-based, thank you for this slide, yes. Any ground-based telescope as ALMA, it looks at the sky through the atmosphere. And the atmosphere is a filter. It filters out some frequencies, and then it is transparent at some other frequencies. So what we look in this picture now, we look at what we call the atmospheric windows. So practically, in this picture, we see the transmission of the millimeter, sub-millimeter waves, the type of radio astronomy we do. The transmission, which is possible in percent through the atmosphere. When you see the curve is very high, that means that the atmosphere is very transparent at that level. But when you see that it goes down, that means in that place it's impossible to see the sky at our frequencies. Then it wouldn't make any sense to have a receiver in ALMA that works at that frequency. That's why we don't build those receivers for ALMA. There are receivers like this, but they work outside of the Earth atmosphere. Usually they are placed on satellites. So for a ground-based experiment as it is, a ground-based project as it is ALMA, we built the receiver matching the atmospheric windows. So there is we have 10 bands from band 1. You see in this plot 1, 2, 3, up to number 10. And also maybe you see that the transmission goes down and down when we go to the larger number of the band, which is the highest frequency. And this is also a reason why when we move to higher frequency, to let's say from band 6 to band 7 or 8 and 9, it starts to be more difficult to do our observations because the atmosphere is less transparent. But that's the reason why, let's say, we put ALMA at 5,000 meters in the driest desert on Earth. So because exactly that's the best sky we can have, and for many nights during the year, we have good chance to be able to have a good transmission from the atmosphere, even the highest frequency.
There are some seasons on the year that are better, no? Which are they? Like during winter time or summertime?
Yes.
What would be the best time for this kind of observations for higher frequency?
Right. So it's a very good question because it's a fundamental question. So because we should mention that ALMA is not a static array of antennas. It's a dynamic array of antennas. We have two transporters. They are able to lift up the antenna, which is 110 tons, and transport it kilometers away and put it in a different platforms. On the plateau, we have 66 antennas. Of these, 12 of them, they never move because they are the 7-meter antenna for the compact array. But the other 54, practically, we move them around every second month or something like this, and we change the configuration of the array. The reason why we do this is to put the antennas more far away in a way to have more baseline, more distance between the antennas, which means the telescope is larger and so has a better resolution power. Or we put it in a compact shape. We put the antennas all close together in a compact place, and then we have more coherence between the antennas. So the trade-off is between, let's say, is the type of science you want to do. If you want to do a type of science where we need very high resolution, resolving power, then you have to put the antenna far away. But the problem is if the atmosphere is unstable, if the atmosphere is turbulent, you don't get coherence. So we are not able to do this interferometry, especially at high frequency. So it is related somehow. And there are periods of the year, especially between, I would say, when it's very cold, let's say July, August, when the sky can be very stable and very transparent. But of course, it's a trade-off with the weather because sometimes there are very strong snowstorms I think it is happening it had just happened a few days ago, right? There was some snowstorm up there. So it's a bit tricky. And from my experience, the best time actually is during spring, between the Chilean spring, right? Especially October and November. I think between the month of November is the one where there are the best conditions, because it's not yet summer, so the site is still very cold, but it's not winter anymore. So there is no much wind or turbulence. The sky is more stable. And in that case, we can do really good observation. Unfortunately, then getting into December and January, when it is summer, the humidity goes up, and also there is the monsoon, right? There is the seasonal, the altiplanic winter. So in that case, we really put all the antennas all together, all compact, in the smallest possible configuration, because that's the only one that can work in that condition.
Taking care of each other.
But then in the other part of the year, slowly we try to expand the array and to get in the largest baseline.
As we see those triangles in the video, those are the paths, so they change the array accordingly. Yeah. So taking a little bit from the question that we received, I would like, for the public to know, what are the futures for the case in the receivers and the case, of course, of the correlators? If you have any upgrades that are coming, you can tell the public about these new technologies coming.
Well, there are many. Well, we expect that for, let's say, in 10 years more, we have a new observatory. But it implies
a lot of
things. Yes, it's a big challenge. Yes. There are many projects that are ongoing. Well, they are still under a plan, but the idea is to increase the number of the bandwidth we can process in the antennas. We need to increase the number, all the transmission chain of the data. We have to increase the capabilities of the digitizers. The correlator itself needs to be replaced completely, because most of the data requires a huge amount of processing. And we have now new technologies that allows us to process much more data.
So it's coming an upgrade for the correlator, because now it has over 10 years, no, that has been built. So for the technologies now, it could be running in a higher processing way, no? So
yes, this is the eternal issue. We have to start planning, then we start testing with our present last technology, and then we start to develop a solution that has to be implemented as an observatory. And finally, we start to produce the parts, and finally, at the end, we produce an observatory. But normally, when we finish to produce a new observatory, the technology we are using is already old.
Yeah, exactly.
It's unavoidable.
Yeah.
Unavoidable.
Really.
Yes.
Fast pace.
Yeah. I can add from the side of the receivers, exactly as Lorenzo said. So the plan at the moment is to probably to go to the double of we call this the instantaneous bandwidth. So practically this means the range, or let's say the spectral, the amount of electromagnetic spectrum that the receiver can detect simultaneously during one observation. And this has a lot of implications. So first of all, we have to think that the receivers themselves, they collect the photons, right? They collect the light or the radiation that comes from the sources in the sky. And that's the conversion. It's like a transducer. So it takes these electromagnetic photons and convert this to voltages, usually. Just an electric signal. But this electric signal is analog. And you don't want to send an analog signal in an electric wire for kilometers away, because it wouldn't be able to arrive to the correlator. So what we do, we use what we call the back end. So the receiver are in the front end, which is in front, looking at the sky. Now on the back, there is the back end that takes this analog signal and does the conversion to digital. Mm-hmm. And from the moment it's converted to digital, then you can send it through the network. You can send it to thousands of kilometers away. It doesn't matter. If the network works, you can send it without any loss of information. This wouldn't work with the analog signal. The analog signal would lose information, will be noisy at the end. So we have to convert it to digital and then send it to the supercomputer, which is digital, of course, is able to handle digital signals. Mm-hmm. The problem is that if we double the bandwidth, so we automatically double also the amount of data that has to be in real time, has to be converted to digital. And this conversion to digital, Lorenzo mentioned this at the beginning of that it's already we have gigasamples per second. But when you double the bandwidth, there is a Nyquist theorem that says if you have more bandwidth, then you need even faster sampling. So doubling the bandwidth, it's a challenge. It's not just a factor of 2. I mean, it means we have to replace all the digitizers with something that has to be even faster in the digitization. And as Lorenzo said, when we started the project more than 10 years ago, this capability was not available. There was no technology able to do that. That's why we have the bandwidth that we have. That was the best we could do at the time. But now, finally, we have some, Lorenzo, correct me if I'm wrong, I think we are reaching like more than 40 gigasample per second. Are we in this range now?
Yes, we are
Which
around
is,
that. This is the number we are around.
Yeah. And this is the new technology. This is just coming just since a few...
Translate that for the public. What does it mean to sample that number?
It means that if we are able to use these new digitizers, then we are able to use larger bandwidth. And if we have larger bandwidth, we will have more sensitive receiver. We will be able to collect more photons simultaneously per second, let's say. And so we will have
amazing.
Yes, and also spectra. We can see more molecules. We can see more lines, spectral lines simultaneously. There is a lot of advantages.
Yes, that's the interesting thing, that we are able to observe a wider spectrum, and then in this case we can save a lot of observing time by using this kind of technologies. So our observing times are very expensive, so we have to take care of it.
Yeah.
Amazing. So we have another question from the public. It's coming through there. Let's see. Does the antenna deform at all when it moves from zenith to horizon? Does this affect observing frequency? From Tumby, I think.
Very, very good question. Well, the antennas, I mean, this is very important because as a type of radio telescope, usually we are used to see the Parkes or, I don't know, Effelsberg, Green Bank, this radio telescope, the Arecibo, that now unfortunately collapsed, but it was 300 meters, right? There is a new one in China, which is 500 meters, right? The fast radio telescope. So they are really huge telescopes. In comparison, our single antenna is just 12 meters, looks like a small antenna. But we have to scale it with the wavelength. So for the type of radio astronomy that we do, it is challenging to keep the parabolic shape, to keep a parabolic mirror that works for sub-millimeter waves. up to almost 1 terahertz. Band 10, the highest frequency that we have, arrives up to 950 gigahertz, which is just below 1 terahertz. That's almost infrared, so we are getting to some sort of optical quality when we want to do the observation with this. So even moving the antenna from the zenith to a different angle can produce a deformation of the dish that changes a bit the shape, and then it doesn't really focus very properly. I mean, it doesn't work anymore as a perfect paraboloid. Actually, our antennas, they are never perfect paraboloid, but we try to do the best we can to adjust the surface. There are several adapters, the adjusters, so we usually in the range of 1,000 screws in one antenna that we have to adjust one by one in order to put the surface of the antenna as close as possible to the surface of a paraboloid. And then usually when everything works, our antennas, they are in the range of 10 microns. The irregularity, so the irregularity on average on the surface is just 10 microns over 12 meters of diameter of antenna. This is amazing. It's amazing accuracy. To make an example, in the Effelsberg radio telescope, which is 100 meters in Germany, but the accuracy there is in the order of sub-centimeters. So we are talking several order of magnitudes larger. Sometimes I saw people working on the dish. So there are sometimes people that for maintenance, they walk on the dish. We cannot do that, of course, because we have to keep it at 10 microns from the surface of the parabola.
Yeah, actually,
so it's very challenging for a 12-meter antenna.
Very challenging.
Actually, it's very one of the first steps to set to work an antenna. The first part of the antenna setup was to adjust the surfaces, and it took a lot of efforts.
Right.
To set the surfaces to the desired shape. Also, during the observations, we use a lot of parameters that compensate this deformation and allows to keep a proper signal on the antenna.
So there are many steps after, no, to just be able to get that information with that deformity, no?
Yeah, the idea is that we are also have to compensate the difference because of the position of the antenna, the thermal effects on the antenna, and so because the antenna is deformed also with the temperature. So we have to take care of these stuffs in order to get the proper shape, proper signal.
Right. So perhaps the final answer to the question is that we do not adjust the surface between the observations, but we do, whenever we have the opportunity to adjust the surface, we adjust it in a shape which on average is the best that we can get for the range of elevations of the antenna. The antenna is only rarely looking really at the zenith, and almost never observe at the horizon, right? So we do an adjustment which is, I think, for a range of between 45 and 60 degrees, which is optimized for that elevation of the antenna, looking at the portion of the sky, because on average we most of the time look at that elevation, and it is adjusted with a thermal model which compensates for the thermal deformation in some range of temperatures, which is the usual range of temperature, let's say between 0 and -10, which is at the AOS, where the antennas are located. So this is what we do to try to optimize the surface of the antenna on average, let's say.
Yeah.
Of course, then there is another factor that during the time, the antenna loses the shape for several reasons, just because some plastic parts, they deteriorate, or some deformation is not completely elastic. So with the thermal expansion and then contraction, when this happens several times between winter and summer, or the sun and the snow, and then it doesn't go back to the same position. So periodically, we do monitor the surface with the technology that we call this holography. So we do a map of the surface. We can measure actually the deformation of the dish, and whenever the deformation is too high, then we do a campaign to send people with the screwdrivers. They have to fix the panels and put it back in the correct position.
And
It's a lot of work.
It's a lot of work.
It is.
Yeah. It is
Yeah.
a lot of information too that we have to get through for getting to really learn about each of these instruments. And I really appreciate this time that you both have taken to join us. Sadly, we have to close now the virtual tour. We're having another one now in Spanish. So I really want to thank you for being today with us and answering all the questions from the public. And we will hope to have many more of these instances to talk about the instruments of the antennas, the work at the OSF, any anecdotes or more information. So I leave all the public, also the viewers that were seeing or watching us, that we're having every month one of these virtual tours with different guests on different subjects. And the next one is going to happen on August 19. And it's going to be about the transporters, the ones that you were talking about, Giorgio. So then we go on to more specifics of these huge machines too. So thank you very much, Giorgio and Lorenzo, for being with us. And
thank you for the opportunity.
If you want to say,
a pleasure.
Yeah, goodbye. Thank you very much.
My pleasure.
Bye
Bye bye.
bye.
Bye bye.
Thank
everyone.
you.
Ciao. Bye bye.
Bye bye.